Hi, Victor. I think that you have a problem with your microphone.
I don't listen anything.
No. No.
I'm not listening.
Victor,
No. It's
we are
a
not
problem
listening you.
of the Victor Microsoft micro.
Zeta also.
I leave the.
Do you listen me? Any of you?
Yeah, I listen you, Ismael.
Oh, okay.
I think it's a problem with Victor's microphone.
Okay.
No. If you
Now?
Victor, I hear you.
Okay.
Hello?
Now, yes. It's working
Yes.
now.
Okay, let me just adjust my volume. Okay, so you can hear me properly now?
Yeah.
Good.
Yes, I do.
Okay, so as I said, let's first go to our Hpc portal that you can find this address, hpc.thesuk.cat. And it's essentially a one-stop portal for two very important things. First is our support tool, our ticketing tool, in which you just have to register to see to be able to raise a request or to see your tickets, but where you can just perform any question, any report any incidents, ask us about anything. We'll go back on that later. And the second is the documentation one. So in the documentation, you can find a specific part which is related to what we did today, which is the training section. And here you can see the presentations that we will update with today's slides soon. And also in this practice section here, you can see essentially what we are going to do now, which is just a brief introduction that I'm sort of explaining to you, and then a number of hands-on just to illustrate some of the ways to interact and work in the cluster. So back to the ticketing tool, to our service desk. If you are not registered, you can just sign up for an account. This is completely independent from the account in the machines as an actual user of the cluster, and you can do it just to ask us a question or anything else. And let me just go very quickly to my own account. Let me log in just to show you what does it look like? Sorry. This one. Sorry for the delay. So here, this is when you're registered in our ticketing tool. This is what you can see. And here you essentially have two ways, two categories of requests to raise with us. Technical requests, which are the ones you typically deal with as an end user. Just report an incident. Is a job not working properly? Have you found something that is incorrect? Is your application throwing up a message, an error message that you don't understand, so on. You can also request new software, an application, a library, whatever it is. If you want us to help you understand something, or maybe look into how much of an improvement could you get from applying something to your application and so on. This is sort of for longer term, more specialized support. And just for general technical questions. And we also have a second set of requests that have to do with administrative tasks, such as, do you need a new user in your group? Do you want to renew? Do you want to buy more hours for using our machines? And so on. So whenever you open a request in our system, you will get email confirmation, and by default, you will get an email when an important change in the status happens to that ticket. You can personalize this. You can get as many or as few emails as you want, and so on. And this is pretty much the main window through which you can contact us. Anything you want to ask to us, you can just drop us a ticket here, and we will be more than happy to help you. So you will have a username and a password for the hands-on. Is that correct?
Yes.
Okay. So let's go and connect, which is pretty much the same thing we would do if we were new users. Let us connect for the first time with this username and password. So it's as simple as SSH. We need to use port 2122 to connect to our machines.
Da come senti?
And then your username, which will be in the form course something, at hpc.cat. Okay, so the first time you connect, you have to introduce your password. And when you introduce it correctly, a mechanism triggers to force you to change it. So we don't know what your password is. So immediately after connecting, you have to introduce the same password again, so the one we gave you. And then you have to introduce a new password, which has some restrictions. It has to be at least 8 characters long. It has to have both uppercase and lowercase letters. It has to include numbers, and it has to include special characters such as, I don't know, parentheses, slash, underscore, percentage, and so on. So you will have to choose a valid password with all these characteristics. And then your session will be automatically closed. This is what happens if you put a password that is not good enough. If it's correct, you have to retype it. And then it's closed, which means it's actually fine. You have successfully changed your password. So you connect again. And then you will see these messages and your prompt. You will be at your home, which is /home/ your username. And then just standard console environment. I'm guessing most of you use Linux, so you probably don't need much introduction to the basic commands. If not, ls to show files in the present directory, cd to change to another directory, and well, pretty much cp to copy, mv to move. You can look it up in any basic Linux guide online. So this is what you need to connect, but you probably in your work, you're going to want to transfer files from your local system to our cluster and vice versa. So how do you do that? Let's close this connection. And then the simplest way is to use scopy, SCP, which is simply copy over SSH. So you're copying over your secure connection to the cluster. If you remember, this is the SSH command. To copy files, it's very similar, but instead of SSH, we use SCP. The port option is uppercase, not lowercase. And then you have to specify a number of local files to upload, and to tell SCP, to tell secure copy that you are not copying locally, but to a server, you have to add a colon at the end of the server name. And if you wanted to copy from the cluster to your local machine, you would do exactly the same. First, the host name, colon, always the colon, then the path of one or more files on the server, and then your local path. For instance, if I want to copy on my desktop, I would use home vbred, which is my username, desktop here. And for instance, let me open a second terminal just so that you can see what I'm doing. Sorry. For instance, to copy that README file, I would simply add README here if I'm working, if it's on my home directory on the cluster, or just a full path if it isn't. Okay. So have you all been able to connect, change your password, and move around a bit? Are you all connected to the cluster? Can I get some
Yes,
yes,
in my
no, some
case.
chat? Yes.
In my case, yes.
Yes.
Okay, brilliant. So I'm going to leave you with Christian, who's going to do the first of the hands-on,
Okay.
and then I'll see you later.
Okay. Share screen, desktop. Hi everyone, can you see me? So I'm going to start with the NAMD tutorial. First of all, I go to the webpage, hpc.cat, and I find NAMD hands-on. Okay, so here is the instructions, and you can download here the sources, the files. Download. Okay, and the file is water.tar.gzip. So I'm going to overlap to the cluster with a copy command. Copy dash port 2122, port in uppercase 22, water.tar.gz. And I'm going to upload it to my Scratch. It's uploading. Okay. Now I'm going to log in the machine. Going to delete this. Okay. With my user, the host, and let's go. Here, I'm in my home, and I go to Scratch. I use change directory, Scratch, my username, and here should be the files. Water. Okay. Okay, to uncompress that file, I use the tar command. Extract, gzip, verbose, and file, and it's unpacking, and that's it. Let's join water, ls, list files. I have a lot of error files. Okay. I will remove it to avoid that files and unpack again. Okay, that's it. So let's go to the method. I'm going to enter in water standard with B editor. That are my inputs, NumD input, the water molecules, etc. And it's what I find. The partition, standard fat. No. My partition is standard. I need 24 tasks, so I change this number to 24. I use the reservation course, so batch reservation course. And I think that's all. Modify the water to work on Scratch directory. So move to Scratch directory. And I should move my inputs to that path. So in fact, only I need 3 files. So copy that to my Scratch. And let's go to Scratch. And so NumD is an MP application. I should use srun. Okay, run NumD to the input file, and the result is goes to the standard output goes to water standard. Okay, and modify water to remove the output of the correct. Okay, try to move the output for the correct output inside the original. Okay, so for that moment it's enough. And I think the time, I have to put the time because it's mandatory. Batch minus t, 10 minutes. Probably will finish before that. Okay. And make dir, because I have to move the output to a folder current outputs inside the NumD tutorial. So make dir Scratch and outputs. Copy water standard out to the output. And that's it. I think that it's done. I think should run. Let's check. To launch the job, I use the sbatch command and my slurm file. And boom. Okay, it's running. That's my job ID. So to check what is the state of my job, I use the skew command. Job ID. The flag J is job ID. And check it. It's running on Pyrenees 47. So let's look at Pyrenees 47. I go to the bottom part of the screen. If I running a job into a node, I can log in that node. If not, probably you will be banned. Okay, 27, no, 47. Sorry. Top. And it's running. So I said before, NumD is a MPI application, so it expounds 24 processes, independent processes, which are working together to get the result. If I go to the Scratch directory, that should be tmp, my user, my job ID. Here are the outputs. I can check in real time the outputs using the command tail minus flow. And check the the job on real time. So I don't know how it's taking time. Okay, 2 minutes. It takes, I don't know how many steps should take, but we can, even during this running, we can modify a new file and go to next part. So I made a copy of my.
Christian, can you please show the Slurm file, the Slurm script again?
Yeah, I'm going to do this. I made a copy of the original. Okay, water standard to water standard to 48. Okay, and that's the original Slurm script. Okay, I can explain again if you want. Okay, that's the partition, standard partition. Okay, number of nodes, 1 node. Number of tasks, 24 tasks. The reservation for the course. Okay, the job name, the job that you will see in the queue. The output file, the error file, and the time for the job. Now, that's are the Slurm directives, the resource requesting. My script, I load the module to see NAMD and use it. I copy my input files to my Scratch directory. I don't know what it is, but it doesn't matter. I go to that Scratch directory. Okay, when I'm in with that files, I launch NAMD. That's the input file. That's my executable, NAMD2. And that's my output file, standard output file, okay? Done this, I make a new directory that should be in that path, and I copy the results to that directory. I think it's enough, or I can, if you have some doubt, please ask. No? Okay, I go for file and LL, and I don't know, here that's the output directory which is created by the job, and there's nothing. Okay, nothing copied. Okay, something should be copied, but let's check the error file. If something happens, will be written in the output or in the error file. What's the error? Okay, it's a directory. Thank you. Bueno. I don't know what happened, but I'm going to, let's pass to the next step. I'm going to modify the file to run on 48 cores. So I go to the 48.
Christian, this is a suggestion in the chat about the problem. There was a
oh,
piping.
yes. Thank you, a tipo. Here, yes, it's here. Yeah, it's strange. Okay. I'm going to change the original, but I completely. Yes. Sorry, I'm blind. Okay, I think I modified for 28. No, I changed it to 2048. And okay, it's okay. Well, I assume that it's obvious that if I change to 48, we'll finish before. But I'm going to do it. Batch. Yeah, I use the sbatch command. I provide the file. If you do the same operation more than one time, for example, to making the directory, don't worry, because if the directory exists, only will probably say something in the error file, but don't erase the contents of the directory. Okay, so it's quite flexible in that sense. Okay, let's go to the GPU version while it's is running. Let's check that everything is fine. Here, Pirineos 49 again. 49. Let's check it. The node should be full. Okay, it's full. It's full of NumD2 processes. You can check that the CPU is running 100%, so okay. And that's the memory that is spending each process. That is not too large, probably 1 giga or 2 gigabytes. And the load average, that number should never be greater than the number of CPUs. In this case is 48. If you see something that 52, 16, something is wrong. In that case, in that concrete case. Okay, so let's do GPU version. So I'm going to copy the original. That is the water standard, and I create water GPU. It's quite more difficult. Okay, first of all, the partition. It's not the standard partition, it's the GPU partition. Okay, I'm going to change, so it's sure that it's going to the job will run in a GPU node. More things, 24 tasks. The jobs should request in multiples of 24. So now it's at 24, one node, the reservation same. I'm going to change the output files to say that we are in the GPU node. And the most important in that case is specify that I want a GPU. That is with that keyword gres equal GPU 1. So I requesting 1 GPU by 24. If I put 48 cores, I should put 2 GPUs and vice versa. Okay? But there is one difference between NAND in GPU version or MPI version, that NAND2 for GPUs is not MPI. That only can run only in one node. So I delete the srun. I will change that the output. And I change again. These kind of things could be done more efficiently and more automated, but for the beginners is quite easier to do step by step. Okay, good, and I'm going to see if there is a result that I think it's finished. The other, yes, it's finished now. 44, yeah. So I'm going to launch the first example. Let's batch to the GPU where okay, here and launch. Okay, running, and that is important to see skew the GPU if I have time, because I think it's too fast. Pirineos GPU 3, GPU 3. Well, it's configuring, so it's in idle, it's in power save mode, so it will takes 2 or 3 minutes to start. So when I join in the node, I will check the state of the GPU. Why? If you want to be sure that you are using the GPU, there is a command called NVIDIA SMI that is like a top command for the CPUs, but for the GPU. So I wait if I can join the node, because it's power off, it's power to save energy. And it takes 2 or 3 minutes. Wait again. So don't worry, because it's not a problem. It's a politics of the CSUK in we are green. And then I don't know if there is another. No, there is no questions. I don't know if you have some questions while the node is powering up. And it should be just the last step. It's in fact, if your application it's not nothing strange or in a bizarre parallelizing methodology, it's really easy to launch a job. Only you have to request the amount of memory, the amount of cores at the time, and it will run same as a personal computer. Here we are top. And think it's starting or it's dead. No, it's configuring. And we'll start. Let's wait. Let's wait. It's loading. Now it's starting here. Now, if you see, there's only one process. Okay. But if I type NVIDIA SMI, I will see that there is a process called NAMD2 that is using 14, 6, 10% of the GPU. The other NAMDs with only cores took around 4 and 5 minutes. It will take less, I think. No, depending on the problem, but in general, the GPU is 8 times faster than a node, not a standard node. I think it's finished. Okay, yeah, it finished. As I said, it takes only 30 seconds. The most part of time it's spent powering up the node. So you can compare that the time is absolutely different. If you can compare the results using the ESACCT command and check the long version of the command, and there is a lot of fields to check. You can select, for example, output elapsed. I think there is a lot of output. There is a lot of format. There is a lot of keywords here to compare. Job ID. The first one take 2 minutes, 3 minutes, 50 seconds. So it's twice. And for me, by my part, that's it. I don't know if you have some questions about that easy and short hands-on. It's a way to start. If not, I will pass to Ismael, I think, no?
Yes.
Okay, so it's for you, Ismael. The floor is yours.
Okay, thank you. Well, I think that there is no question about the part of Christian. No, okay. So let's have a look to the hands-on about Gaussian. Okay, it's a Gaussian. Let me share the screen, because if not, you are not going to see anything. Okay, do you see the screen? I suppose yes. Okay, thank you. We are going to see the Gaussian hands-on. Okay, it's a hands-on that is divided in 4 parts. So we are not going to do all of them because the two first parts are very basic and are quite the same as the part that Victor said that has done in the initial, and then the second one is the submit of a job using Gaussian, but the mechanism is the same as the job that has submit Christian. So we're going to go directly to the arrays in order to see, to show you how can you use arrays, okay, and why are quite useful, okay. For this, you will need to download the files about, well, these inputs, these Gaussian inputs, okay, that you can find in the Weiming the environment, the number 0 of the Gaussian part, okay. Download them and you can update them into the cluster with the scp command as Christian and Gaussian and Victor has done before, okay. And we will pass directly to the caffeine part, that is the number 2, okay. That it's basically it's a comparison between different functionals. If you have used Gaussian and you know more or less how computer chemistry works, well, it works with some functionals and some bases, okay. We will try to change these functionals and these bases in order to see if the results are in order to do the same work as some investigators have done in the paper, okay. Here at the end of the hands-on, you have the reference to this paper if you want to read them later, it later. So so let's start, okay. You will need to connect to the cluster with the graphical interface activated, okay. That is adding this /x flag into the SSH command, okay. Because we are going to use a command to see the molecule later, okay. So once you have updated the files, I don't know if you have done it now, if you are okay. I have done it previously, so I can go to the training in caffeine, okay. And here I have the input file of the caffeine, and I have prepared a caffeine.slm that is the same, it's this version of here that is you have available in the website, okay. Oh. Okay, and you have to be sure that that this script will work, okay. So you have to check if there is any error or not. So to go a little bit faster, let's check it line by line, okay. First of all, we need to put the shebang, okay, this line of here that is not in the example of the hands-on, okay. Let me put it in this way. Okay. So this is the first part, okay. Then the exercise asks you for some characteristics that you have to ask to the class, to the swarm, and some parameters that you have to put in the script, okay. The exercise asks you to generate an error and an output file that has this pattern of here, okay. this pattern here, it's not necessary that you write it by hand, because first, because the job ID it's not given until the submission of the job. So in this moment of that, you don't know the job ID. Okay. So you can put this percentage A and percentage A capital letter and a small minuscula, okay, in order to give the reference as the job ID and the task ID. Okay, the task ID, if you remember from the explanation of this morning, task ID is the element of the array. Okay, so for the first element of the array that you submit to a job, this job will be named, well, this file, the file that refers to this job, will be named as caffeine, the job ID, and 0. Okay, and the second one will be caffeine, the job ID, and 1. Okay. Then we need to ask for 2 cores, because this calculation will be in parallel. Okay, and these 2 cores are we need to ask them with the CPUs per task, because the parallelization of Gaussian is parallelization is an OMP parallelization. It's not an MPI parallelization like NAMD, like the calculation that Christian did before. So we need to ask 1 task and 2 cores. Okay, is the minus n is the number of tasks, and the minus c is the number of the CPUs per task. Okay, we'll need 2 CPUs. Yes. Then we will need to specify a 75% of the memory for Gaussian, or the all memory available. 175% will be for Gaussian, and the other 25% will be for the system and for Gaussian, in case that that the memory fluctuates. And to avoid the killings of our job because of lack of memory, we are going to ask a little bit more than the memory that we are going to use. Okay. So for this, we can specify a variable. Okay. We are going to pass all these parameters, the number of cores, the functional, and the memory, not in the input file of Caffeine, but by command line. Why? Because it gives an opportunity to use arrays without the necessity of duplicate the same input file of the Caffeine, but only changing the methodology. Okay, and only changing the functional and the base. Okay, so we define a variable with the number of the Slurm CPU that we are going to use, that it's defined in this environmental variable that Slurm sets when the job is submitted. Okay, in this case will be 2, because we are asking for 2 cores. The amount of memory per core, okay, that is default, and a 75%, okay, and a 75. Then the number of cores is as I say is the value of this environmental variable, Slurm CPU per task. Okay, you can use it, and it refers to the number of cores that you are using in the job, and we are going to use these both variables inside as a parameters for the Gaussian. Okay. Then we need to specify a proper time limit, less than 45 minutes. Less than 45 minutes. Of course, this will be so too much, but well, it's a way to be sure that your job is not going to be killed. Okay, as a priori we don't know how much this calculation will last. Let's let's be generous and take some, put some time, the more. Okay. So here we have the dash t and 45. That means 45 minutes. Okay. Then the working directory properly. So we need to use Scratch as the working directory and not home. So for this reason, here we are going to copy our caffeine input into the Scratch and move us into the Scratch, okay? And we are going to use the slurm job arrays, okay? One way of achieve this is make use of the case, of a case. This is a bash case, okay? How does it work? I don't know if you are familiar with case, but it could be really useful for this kind of situation. For example, this variable, this environmental variable of here, the slurm array task ID, is, as I said you, the number of the task, the number of the element of the array that has been submitted. Okay, that it's calculating. Okay, so for the first element of the array, we are going to use Hartree-Fock, okay, with this base. Okay, for the second element of the array, we are going to use Hartree-Fock, but changing the base, and so on and so forth. Okay, so this is a way of submitting 12 calculations. Well, 12. You are submitting only one calculation, one job, but truly you are doing 12 calculations. Okay, and this is only a backup in order to avoid some strange behavior. Okay, how can we specify that we are going to use arrays? Well, with the less a, well, slash a or slash array, okay, and the indices of your array from 0 to 11, and you will submit 12 calculations, 12 jobs. Okay. Of course, you can put here whatever you want. You can start from 1 and finish in 12, but in general, the most common methodology is to start from 0 and finish in endless as 1. Okay, and here there is one limit that we have to limit the number of arrays that are calculating at the same time. Okay, we can do it with this percentage symbol and the number of arrays that should be calculated at the same time. Okay, so we submit the array. This array will transform into 12 different jobs, and only 6 of them are going to run at the same time. Okay, and the other 6 will pen in queue. Okay, and finally, we have to generate a log file with the job name. Okay, job ID and array task ID. And again, we can use these environmental variables. Okay, slurm job ID for your job ID, and slurm array task ID is the same that we used in the case. Okay, and this will generate us 12 different logs, 1 for each calculation. Okay, this is only a way of doing. You also can, if instead of having only one input file and doing this by command line, you can generate 12 input files and reference all of them by a number, for example, that is identified with the slurm array task, or even if you are more expert or more prone for things like that, you can generate a bash array with all the inputs in the directory, and then access to this array with the slurm array task ID. Okay, it's quite more complicated, but it's also a solution. Okay, and finally, we will copy the result. We only want to save our log file to our submit file, okay, where we have submitted the job. And for this, there is also another environmental variable. This is slurm submit there, and that's it. Okay. So we are going to see, we are going to try if this works or not. Okay. So we can submit this job to the queue. There is only one job that we have submitted one job with this job ID. But if we run an SQ with our user, we will see. Okay, wait a second, please, because I forgot to specify the reservation. Okay, as the cluster now is a little bit grounded by jobs, we have done a reservation in order to go faster. Okay, let's cancel a job, and this will cancel all the arrays. No, not all the arrays, but okay, only the arrays that were pending. Well, let me put the reservation with not capital letters and course. Okay. Then let's see now. Okay. We have 12 arrays, 12 element arrays, okay? One job with 12 element arrays, and 6 of them are running right now, okay? And the other 6 are pending because we the limit of the 6 element of the arrays has been changed, okay? So let's see. Oh. 7, 8. For example, this one. Okay, there is no warning. So this is running, it seems. Yes, this is running. If we enter to this node, the Pyrenees 47, we should see and execute a top command. We should see our calculation, our processes. Yes, here they are. 1, 2, 3, 4, 5, 6. Okay, 6 processes. Well, the system has invited me to go out the Pyrenees 47 because my jobs has been finished. So I have no permission to stay in the node after my calculation is done. Okay, and here we see this log file. Okay, well, the log files are being copied. Okay, so now we can see the result of this calculation. Okay, if we do a less, for example, that is for see the content of the file with the this one, for example, and we go to the final of the job, you can see that the calculation has terminated normally, okay? And this is only for one of our calculations. But here we can see that the 0 it's also calculating, but it has been also calculating, and so on and so forth, okay? So now we can start an interactive job in order to check graphically this calculation, okay? For start an interactive job, we have to use the salloc command, okay? And we are going to use the graphical interface. So we need to put this flag of here. The time, no more than 10 minutes. And the reservation course. So we are here now inside of the job, inside of the node, okay? Node Pyrenees 47. So we are now inside of an interactive job. Here we can work as inside a job, a normal job that we send to the queue. But in this case, we are doing the job, okay? So we load the module for our program that will permit us to see these results, okay? We'll load Molden, it's called Molden. We move to the training caffeine, okay? And we will see the number, this one, okay. We have to wait a minute, moments. And the system open a window, okay, for with the results of the calculation, okay. We can see here, I cannot move this. Okay. We see here the evolution of the energy during the optimization of this molecule with this functional and with this base, okay. And well, this is only the, and we can see in directly how the atoms are moved. It's quite basic chemistry, but it can also be done with another kind of software, okay? So I hope that you find this useful. The use of arrays is a really powerful tool, depending on your calculation, your kind of calculation, your kind of jobs. But if you are some calculations that are like this, that you have to do a calculation, the same kind of calculation on a lot of inputs, it's worth taking some time in order to make an array instead of submitting a bunch of independent jobs to the system, okay? So, is there any question? No? Okay. You have this training in the website. So if you want to look for the other parts of this Gaussian Hands-On, you are free to do it, and they are quite good. Okay. So thank you to all of you, and I think that I'm going to pass. The next one will be Victor with the Conda. With the Conda, I can see. Okay.
Let me just take over the screen. Much like like Ismail was saying, you will find that these hands-on were originally intended for when we could do these courses in person. So they're intended for you to take your time and go through them step by step. So with that in mind, and knowing that the installation of a Conda environment, particularly if it has many dependencies, can be a long process, I'm just going to show you how to do it, but I'm not going to wait until the installation is complete and to run the jobs, because essentially the job running part is exactly the same as my colleagues have shown you, and it will be just pointless to wait for many minutes. I'm going to show you how it is done, but I'm not going to wait for it. So if you go to the Conda hands-on, here you have a link to the Conda documentation and to our presentation that I gave you this morning. But what's more interesting, we have standard compressed file with everything in it that we need. So let me just download it and then copy it. Let me go a bit more slowly through this. So minus uppercase P. Here will be the file, but my username is course 60. So like this, if I don't put anything at the end, it will just go straight into my home. And then here, I'm looking for this file. So it's up. Let me connect to the cluster. And here we are. I decompress the tar file and we get a small list of files that we're going to use in essentially two exercises. The first of which consists on, it's not, yeah. In the first one, those two exercises try to show the typical situation you're going to find yourselves when trying to run something through Conda in our machines. The first case, you know the script, you know very well what it does, you know very well what you need, and just simply need to define your environment, what you need in your environment to run them, and also the script you're going to use to run them. So, for instance, we have a script called, let me just close this, script called 1.1.py. Okay. So what we have essentially here is a number of FASTA sequences that we are going to compare and do some very basic things with, just to run some Python code on it. We know, because we did it, that we need BioPython. Then we use, at some point, we use matplotlib to do a plot. And the rest of it is just part of the core Python installation. So let's say we're going to do a new environment. What I will need to do is as follows. I have nothing on my environment. So the first thing I need to do is to load the environment module for Conda. Like this. No, you will notice that you get a message saying that a configuration file has been sourced and it won't be reversed. Normally, when you load an environment file, and everything you do, every change you do to your environment variables and so on is reversible. With recent versions of Conda, this is not so. So this is just warning you that if you do module unload Conda, you're not going to get exactly the same environment as you had before, because there are some things that won't be able to be reversed. That's all. So the first thing I will need to do will be to define what I need, which is these three things: Python, Matplotlib, and BioPython, and then create a new environment to host them. I can simply create an empty environment. Sorry, create an empty environment like this. Let's say I call it. Oh, there's a. Let me reconnect because I don't like when terminal doesn't work properly. Just 1 second. Here we are. Okay, module load Conda current. Again, it's a message, but now it's working properly. So I could first use Conda create -n 1.1, for instance, to create an empty environment. It will take a bit. It just checks that there's nothing strange there, that the folder is correct, and so on. And as you can see, the environment is created in Scratch. My username, .conda, env, and the name of the environment. But this is an empty environment. If I activate it, you will notice that my prompt has changed to show the name of the Conda environment I'm using. If I do Conda list, which is to show the packages in it, there's nothing. So what I will need to do is to install. If I don't specify, sorry, in which environment, it will be in the one that's currently active. So that's 1.1, which is exactly what we want. And I need to specify at least the 3 packages I need. You might not always be sure what's the name of the Conda package that corresponds to either a Python module or an R package, because they are not exactly the same. Easiest way is just to Google it. I mean, Conda has an excellent webpage listing everything that's in there. So if I Google Conda Matplotlib, the first result I get is for the version in channel Conda Forge. Do you remember what I told you about channels before? Which is this one. Here I can get a lot of information. I can see bills, I can see history, I can see, I can download whatever I want, and so on. But there's a general trend that's useful to know, and that is because Python modules were the original intended target. Sorry. These typically keep their name. So their Conda package is called the same as the Python module. For instance, here, Matplotlib. R packages are typically preceded by an R dash. So for instance, a pretty standard let's go for R base, which is the basic execution. Everything which has R dash will be an R package, except for those which have which come from bioconductor, because bioconductor essentially does a whole new repackaging of everything. So those are preceded by bioconductor, and then dash, and then the name of the package in question. Okay, that's just in general. Sometimes for very strange packages, or sometimes for system libraries that you are using as dependencies for something, you might not get the same name. It's very easy to find what you need to install. In this case, I need Python, I need Matplotlib, and I need BioPython. However, I could be more specific. If I do this, the environment is going to get 3 specs, which is what they're called, which is 3 things that I'm telling the environment to include no matter what. Everything else will be dependent, and so could be removed, changed in different ways. But the specs are going to be the center of the environment. And specifically for Python, the system will never try to force you to update it unless you want to. For instance, I could specify versions. If I wanted to, for some reason, wanted to work with obsolete Python 2 code, I could specify Python 2, even though it's no longer supported. But I can also specify subversions. I can be as specific as I want, and as long as it's available, everything else will change to fit that. If I did some impossible combination, it will just not let me install anything. Or if I was doing an update, it will not let me update anything. And it will explicitly tell me which version conflicts are preventing it from doing it. So what I will do is this. It will immediately start collecting the package metadata from the remote server, and it will just install a long list of packages, most of which are simply dependencies of one of them. You can see, for instance, that BioPython that I asked for is going to be installed in version 1.78. And we're going to get Python 3.9.2 as well. So if I say go ahead, it will simply start downloading and then installing them. But since this is going to take quite a while, I'm not going to wait for it. I'm going to go ahead, and then you're going to have these users available for a few days, so you can just test by yourselves, make sure you're getting every step in the process, and if you run into any problems, just let us know. You have, in addition to the training materials, here in technical stuff, you have our details. So for instance, if you have any specific conduct questions, you can just drop me an email directly, and I can try to answer your questions. Okay, so exactly as I did before, if you remember when I activated the environment, if we let the installation go through, it will take minutes, probably quite a few minutes, because the list of packages is quite long. And I could simply activate it and have the executables in the environment put in my path, the libraries in my library path, and so on. Let me just show you how it works without losing time. There's one environment that's visible for everyone, which is the basic environment that essentially provides the tools that Conda needs to run itself, which is the base environment. Sorry, if I do Conda env list, which is the way to ask the system for the list of environments I can use, I see there's 1.1 and there's also base. Let me just show you that the change actually happens. If I do which Python right now, I will get the system Python. I always forget, yeah. If I use, if I activate base, for instance, I will simply get the Python in my environment as the default one. And with Conda deactivate, I go back to having no specific environment. And so I'm back to my system executables. Okay, so that's the environment we need. And now we need to look at the script I need to submit to Slurm this job. If you remember, we're trying to run this script, which is a Python script, pretty standard Python script. So what I need is extremely simple. Let's go for this file name, okay? And what do I need in this script, which is meant to be sent to Slurm? First, shebang, to make sure it's interpreted correctly. And then the sbatch options I need to add. As we saw before, for instance, since we are not going to parallelize this, we can go for just one core. I will need to specify partition. I will need to specify, in this case, because you're using a reservation for the course, I need a reservation. Otherwise, I wouldn't need it. I need to add a time, but I personally, I don't like adding time here. I prefer to add time when I'm submitting it, because that allows me to change it more often. Otherwise, you could end up with a short time in a script and just keep running it until you change it, because you're at the moment of changing the job and sending it, you're not paying attention to it. But that's just me, and of course you could do that with any of the sbatch options, so that's completely up to you if you want the flexibility of command line options, or do you prefer the standard way as a comment here. And then what do we need to do for running the script? Let's start with a very simple copy of the script to the working directory, which is going to be Scratch. And if you notice, let me go for this. If you notice the instructions, there are 3 input files that our script reads that need to be copied as well. So we simply need to add those to the list. So we're going to have all 4 files, or 3 input files plus our script in our Scratch directory. if you remember from this morning, if we are just running it in one core, we're just running it in one node, and therefore by default, if we don't specify otherwise, Scratch will point to the local disk of the node it's running in. So to check intermediate files where they're being produced, we would need to do an SSH connection to the node. And of course, as you know, you can change that by specifying that your Scratch has to be local or shared to go to BGFS or to go to local disk. Anyway, I have copied my files, and I need to load my conda environment. Simple as loading the conda environment module, and then activating my environment. As simple as that. And here I have my environment completely prepared. The file is not an executable, so I need to call Python as interpreter. And if I want to direct my output somewhere, I would just do something like this. If I don't specify my error and output files for the execution of the script itself, which is, as you remember what we commented on before in terms of the different outputs of a job, I will simply get them in the same directory from which I've sent the script and with the job ID as the name. So in this case, I'm not going to worry, but it's always useful to have them properly labeled and stored. And that's pretty much it. I don't need to do anything else. Files will be copied. Well, I can copy back this to my home and just get the output in a more convenient place. And it will be as simple as this. Let me move this because yeah. And for the second part of the first exercise, it's exactly the same, but with an R script. Let's have a brief look at it. Okay, so this is an even simpler script that does a number of statistical operations on some input files with data. In the case of R, dependencies are not so clear cut, and sometimes you might be surprised by what you need, but you can always simply just try running it, and R is quite verbose and quite explicit in what it needs from you. So if you just run it, you will see that you need a number of packages, which are listed here as well. No, it's missing. Sorry, I will add it in a minute. And essentially, you have to look for either library or require commands in R, which are the commands that load libraries. But it can be done in different ways, and it's not always so transparent. So sometimes it can surprise you. And as I mentioned before, broadly speaking, if this is the name of the R package, the name of the Conda package you need to install is going to be this, but with R dash at the front. For instance, here. Okay. So there's not much of a difference. What we have to do here is simply look for what we need in the environment, and again, produce a very similar script, but this time calling, sorry, this is long. But this time, instead of calling Python, we have two options. We can somehow pipe the script into R, or what is much more convenient, we have R script, which is a simple executable, which acts as an script interpreter for R. So our file would look something like that. Only, of course, we don't need this anymore. We change the references to the file, and there's two additional files we need to copy. So it will be here as well. And that would be pretty much it. We would just install the packages in the environment and execute this script to see what happens if it runs without problems. I invite you to do exactly that, and to look into the scripts in more detail to understand exactly what is it that you're looking for. But sometimes the situation is not quite as clear as this one, and sometimes, let me go here. Sometimes what you have is you have a piece of code that you don't know exactly what it's going to be to require. Either it has been handed down to you from a senior colleague, or you just found a piece of code online that is meant to do what you need to do. Whatever the reason, you essentially have some script that you have to first investigate to see what you need to do with it. What do you need to install in order to run it? And then you have to run it. There's no difference from the point of view of the script, so we're going to ignore that. Just make sure you get used to identifying dependencies, finding how to translate them into conda packages and installing them. For instance, here, this is a rather simple example of machine learning in which you are from a classic data set, which is wine quality from TensorFlow. If you work in machine learning, you probably have done stuff with this or with very similar data sets. You just run, just to make it simple, a neural network, very simple deterministic neural network on this. And essentially, you need to load several layers of complexity. So these dependencies are actually translating to a quite large number of conda packages. This one will particularly take quite long to install. But that's precisely what you can do as an exercise you will see that here you don't have detailed instructions on how to do it, because that's exactly what you can do. You can just take these scripts as a real case example and just go with them. And here you have an example of some part of a pipeline of next generation sequencing. So the sort of things that you would do with massive genomics data, and it's essentially the same. You just have to test and run it, see what you need, do that iterative process of identifying what you need, trying if it works properly, and so on. So it is again left as an exercise. We typically did all of those things in a classroom with us just answering your questions. Since we are forced to do this digitally, we're going to keep the users open for quite a few days. So please try them and let us know if you run into any problems or if you need if you have any question, really. I don't know what's the time? Let me check. I think we're going to stop here.
Victor.
Yes.
Yeah. One quick question.
Mm-hmm.
In that case, that you have a script and you don't know exactly which are the requirements, the modules you have to install. Is it a good idea running, for instance, the Python script locally without the sbatch command? Just to see the errors it throws to the screen.
In our machines?
Yeah.
Not locally, because that has a strong limit as to the CPU time. So if it does any calculation, it's going to be killed soon.
Okay.
But then you can do an interactive job, which is the best way to do it. So let me show you how it goes.
Okay, because I was doing. In fact, I have this project open with you. And I was doing some stata tests, and at the beginning, instead of running through the queues, I just ran the stata mp command with the do file, and well, in fact, it was a very short job, but I just wanted to know if that was the correct way.
If it's very short, particularly if it's you're just testing a few lines of code that you're not doing any calculation, you're going to be fine, because there's a CPU time limit when you're outside the job, but it's small for a computational job, but it's large for everyday tasks. So you can typically compile without problems a program, not a particularly large one, but you can do it. But if you actually need sort of to let the job run through calculating up until it runs into a problem, you might just get cut out. So what you can do then is run an interactive job, which is exactly the same as an SBatch job. You get charged the same, it works, it has the same options, it works, everything is the same, except that you're interacting in real time instead of sending it to a queue. So to do that, you use salloc instead of sbatch. Let me make it a bit larger. Salloc from allocation. And what you're doing when you do this is let me use the
same parameters.
Exactly the same. I do need to specify a maximum time as well. Let me put 1 hour just to be on the safe side. So, sorry, it's not red, it's course. Okay. So when I'm granted a job allocation, the difference that now I have an interactive terminal. I'm in the node, and I'm using my time. I'm calculating essentially. So now I can run whatever it is I want, and the moment I finish, for instance, I'm just working. I get to the error. I'm done. I just close the session, and the job stops. So this allows you to run, especially for small jobs. It's quite convenient to just see in real time what's going on.
Okay, that's interesting. Thank you.
And then you just stop. The minute you find a problem, you just stop the job, and that's it. Yeah, or the minute you are convinced it's going to work, you stop and then send it to the queue, and it will work normally.
Okay.
Since you're put in the queue immediately, if you try to run interactive jobs with many cores, that's pretty pointless, because you will be waiting for resources, and then you probably will not get those resources until you are no longer in front of your computer. I mean, it only works with small jobs.
Yeah, in fact, that's the point. If you only want to fix the dependencies or whatever, it must be a quick job. Okay, thank you very much.
No worries, you're welcome. Any other question? If not, I think we're going to finish.
I have a question, if possible. I know that R has parallel libraries to work, and also I think that Python has. If we will need that, it's better to relay in their own languages parallel libraries, or we have to work with the srun command, or
R in particular is quite peculiar.
Yeah, that's why I'm asking.
It has different backends, and you can sometimes, if you're not careful, you might not even know which of the backends you're using, and you might not know what you're doing. With R, given that it depends, but the sort of code you're running in R tends to be more suited to not very large parallelism, but to maybe run over 4-8 cores. So when I've done things like that, typically the best results I find are sticking to the equivalent to threads or to an MP, and just run it. But it really depends so much on what implementation you are using, what backends it's best suited to. I think it depends a lot on a case by case
situation. Okay.
Situation, yeah. In fact, you can run into problems if you are not careful. If you parallelize at the Slurm level, you can, for instance, end up, without wanting it, of course, running 12 copies of the same calculation in R instead of actually giving it 12 tasks to work with. R in particular, I think it requires time to parallelize properly, but yeah, it really depends on what exactly are you doing.
Okay, thank you.
Okay, so if there's nothing else, I think we can conclude the session. Thank you very much to all of you who joined us virtually, especially to the ones who are still here. And thank you also to Ismael, to Christian, and to Adrian for giving their talks.
Thank you very much to all of you.
Thank you for assisting.
Just one question, if you allow me.
Yes.
How do we get to the YouTube video of these classes? Will you send us because I was looking for that. It's Hook training, whatever. YouTube. I couldn't find anything. Well, a few videos, but how do we find it?
We're going to. We have been recording today, so we will upload them, and we'll send you a way to get them. It's not online now, not yet.
Okay. Great.
Since we have your details, we will just contact you and let you know where you can find them.
Right. Thank you.